Assalamu alaikum. This is lecture 12 of CS218 Data Structures and Algorithms. In the last lecture, we learned how to insert before or after a node containing a certain value in a singly linked list. We learned how to delete a node containing a certain value in a singly linked list. We built singly linked lists. We inserted a tail node in a singly linked list. And we conducted complexity analysis for the running times of our functions. Our topic today is Advanced Linked Structures. We use chapter 9 of book 1 for this topic. The first advanced linked structure that we will talk about is the circular singly linked list. The circular singly linked list is a structure composed of nodes. We have a node containing 56. It points to a node containing 23, which points to a node containing 12, which points to a node containing 64, which points to a node containing 85, which points back to the node containing 56. The pointer in the last node points to the first node instead of being none. The entire data structure can be accessed via a head pointer, which can be pointing to any node in the circular singly linked list. So the head pointer is right now at the node containing 56. If I start traversal from this node, the sequence of traversal will be 56, 23, 12, 64 and 85. But I can keep the head pointer anywhere now because this is a circle and there is no first or last node technically. So let us suppose that the head pointer is at the node containing 64. Then the sequence of traversal will be 64, 85, 56, 23 and 12. If we start traversal in a singly linked list using a pointer x, we can visit all nodes after x, but we cannot visit the nodes before x because there is no way to go in the other direction in a singly linked list. If we start traversal in a circular singly linked list using a pointer x, we can visit all nodes in the linked list. So this is the advantage of the circular singly linked list over the ordinary singly linked list. So the first function that I will talk about is the circularize function. This function converts a regular singly linked list to a circular singly linked list. This function is also a class function of the class list node that I talked about in lecture 10. And it is part of the same file singly linked list.py. So the function is here. It is called circularize and it takes pointer of the object of the class, which is a node. This is my singly linked list. I want to circularize it. I want to convert it into a circular singly linked list. Self points here. First of all, I take another pointer a and I place it where self is, a self. Then I start advancing this pointer until I get to the node which is the last node of this singly linked list. So I run a loop, a while a dot next is not none, a equals a dot next. What will happen is a will advance from the node containing D to the node containing B. And then it will advance from the node containing B to the node containing C. But it will not go any further because here a dot next is none. So we will come out of the while loop and then I will do this line a dot next is self. So I will make a dot next point back to the node pointed to by self, the node containing D. This is what happens, and now you can see that the singly linked list has circularized. If you start from self and you start traversing, you go to D, B, C and then back to D. So what is the annotation of this code? The while loop will run as many times as the number of nodes in the given list. Let the number of nodes in the given list be n, then this function is on. The next function that I want to talk about, also a class function of the class list node and in the same file singly linked list.py, is linearize. It takes a pointer self, which is pointer to an object of the class, and it takes another pointer a, makes a point where self is pointing. Then we start a while loop and we run it as long as a dot next is not self, or as long as a dot next is not pointing to the same node that self is pointing. In the body of the while, we advance the pointer a. When a dot next and self are pointing to the same node, we break out of the while loop and then we set a dot next to none. You must have noticed that I have not shown you any figures here. I want you to draw step-by-step pictures depicting how this function would execute. But I can tell you the annotation of this function even without the pictures. See, in this function, the while loop will run as many times as the number of nodes in the list. And if the number of nodes in the list is n, then the annotation of this function is on. The third function regarding circular singly linked lists is traverse circular. This is also a class function of the class list node and in the same file singly linked list.py. This also takes a pointer called self, which is a pointer to the object of the class. It sets a pointer a to point to the same node where self is pointing. Then it prints traversing the list. Then it starts a while loop and runs it as long as a.next is not self, or a.next and self are not pointing to the same node. And inside the body of the while, it prints the data in the node pointed to by a. Then it advances a. When it moves out of the while, it prints a.data and then it prints a new line, and that's the end of it. Again, there are no pictures here, and I want you to draw step-by-step pictures depicting how this function would execute. Again, even without the pictures, I can predict the annotation. This is a traversal algorithm. It will visit every node in the list. If there are n nodes, the annotation would be on. So, what we are going to do here is, when we have a singly linked list and we want to convert it into a circular singly linked list, we can use the circularize function. And if we have a circular singly linked list and we want to run the other class functions on it, like insert, delete, etc., we can always first convert it to a singly linked list using linearize and then do whatever we want to do. And we have a separate traverse function for the circular singly linked list. This is the end of the singly linked list.py file. The second advanced data structure in the linked list family is the doubly linked list. A doubly linked list is a structure composed of nodes, but the nodes are different here. Each node has an info field and two pointer fields called right and left. The info field carries the data item that needs to be stored in the data structure. The right field contains a pointer to the node on the right of the current node, and the left field contains a pointer to the node on the left of the current node. So we start with the node containing 34. You can see that there is no node on the left of 34, but there is a node on the right of 34, which is 56. On the right of 56 is 78. On the right of 78 is 12. On the right of 12 is 9. On the right of 9 is 23. On the right of 23 is 17. And on the right of 17 is 90. But there is nobody on the right of 90. What I have done so far is I have followed the black pointers. I call these pointers the right pointers. Now I am going to follow the white pointers and I call them the left pointers. So I start with 90 and on the left of 90 is 17, on the left of 17 is 23, on the left of 23 is 9, on the left of 9 is 12, on the left of 12 is 78. And on the left of 78 is 56, and on the left of 56 is 34, but there is nobody on the left of 34. The entire data structure can be accessed via a head pointer which can be pointing to any node in the doubly linked list. It is not necessary that the head pointer is placed at the starting node. No matter where you place it, you can access the whole data structure because you can move in both directions in the doubly linked list. Advantages of DLL over SLL. A DLL accommodates traversal of the linked list in both directions. For deletion, the pointer to the node before the node to be deleted is not required in DLL, and we'll see why that is so. Any node X can be deleted using a pointer that points to the node X itself. We now create a class called DLNode. This class will help us implement doubly linked lists. The class functions are placed in a file called doublylinkedlist.py. Let us look at the init function. It takes pointer to an object of the class called self and the value that you want to store in the node, val. Self.data is val. So first we place val in the info field. Self.right is none. Self.left is none. A new node has just been created and set to the right values. What is the O notation of this function? O1. Have a look at the function called insert right. This function inserts a node containing value on the right of the node pointed to by self. Let us first assume that the node pointed to by self is not the last node of the DLL. Something like this. And self is here. So you can see that the node pointed to by self is not the last node of the doubly linked list. There is another node on the right. We want to insert a new node between these two nodes, and this new node should contain value in the info field. Now I am going to place 3 pointers P, Q and R, and I am going to place them in such a way that P is going to be on the left, Q is going to be in the middle, R is going to be on the right. I have shown the pattern in the first line of the code which has been commented. So P is self, Q is a new doubly linked list node containing value, and R is pointing where the right of P is pointing. Now the red pointers are the right pointers. The right of P is pointing to the node on the right. Make R point to that. This is it. Now, how to set Q dot right? The right of Q should point where R is pointing. The red pointer of Q is pointing where R is pointing. The next line is Q dot left is P. The white pointer of Q should point where P is pointing. And so it does. The next line says P dot right is Q. Make the right of P point where Q is pointing. Like this. If R is not none and R is not none, then R dot left should point to Q. Something like this. Now let us remove the variables within the scope of the function and show you what we have got. We have inserted a node containing value to the right of the node pointed to by self. What is the O notation? O1. Let us look at the insert right function again. This time we assume the node pointed to by self is the last node of the doubly linked list. Something like this. Self points to the last node of the doubly linked list. Again we arrange 3 pointers P, Q, R. P is on the left, Q is in the middle and R is going to be on the right. P points to self, Q points to a new doubly linked list node containing value, and R points to the right of P. You can see that the right of P is none, so R is also none. Now we set Q right to R. Q right is currently none and R is also none, so that is already done. Then we set Q dot left to P. Make the white pointer of Q point where P is pointing. Done that, then P dot right is Q. Make the red pointer of the node pointed by P point where Q is pointing. If R is not none, this condition is false because R is none, so the body of the if will not be executed. Now remove the PQR variables and see the picture. What have we done? We have inserted a node containing value to the right of the node that was given to us. The O notation is again O1. Another function is insert left. This function inserts a node containing value on the left of the node pointed to by self. We first assume that the node pointed to by self is not the first node of the doubly linked list. The node pointed to by self has nodes on both sides. This time We arrange PQR in such a way that R is on the left, Q is in the middle, P is on the right. P points to self, Q points to a new node containing value, R points to the left of P. So here is R. Now we set Q dot left equals R. So the white pointer of Q points to the node that R points to. Q dot right equals P. The red pointer of Q points where P points. P dot left equals Q. The white pointer of P should point where Q is pointing. If R is not none, this is true. Move into the body of the if. R dot right is Q, and this is done this way. So now we remove the PQR variables as they fall out of scope when the function comes to an end. And this is what has happened. We have inserted a node to the left of the node pointed to by self, and it contains value. The O notation is 1. We again look at insert left. This time we assume the node pointed to by self is the first node of the doubly linked list. So there is no node to the left of this node. Again we arrange PQR in such a way that R is on the left, Q is in the middle, P is on the right. P points to self, Q points to a new node containing value. R should point to the left of P. Left of P is none, R is none. Q dot left is R. Make the left of Q point where R is pointing. R is none, so left of Q is also none. Q dot right is P. Make the right of Q point where P is pointing. And then P dot left is Q. Make the left of P point where Q is pointing. If R is not none, the condition is false, R is none. We do not move into the body of the if. When the function completes, the three variables fall out of scope. This is what we get. We have inserted a node to the left of the node pointed to by self, and the O notation is 1. The delete function. This function deletes a node pointed to by self. First, we assume that the node pointed to by self is not the first or the last node of the DLL. So, we have this list. Self points to a node which has nodes on both sides. We arrange PQR in such a way that P is on the left, Q is in the middle, R is on the right. P is self dot left. Make P point to the node on the left of self. Q is self. R is self dot right. Make R point to the node that is on the right of self. If P is not none, this is true. P dot right equals R. Make the right of P point where R is pointing. See how this works. If R is not none, this is correct. This is true. R dot left is P. Make the left of R point where P is pointing. See this change? Look at the node pointed to by self. You will see that no node in the doubly linked list points to it. So effectively, the node pointed to by self has been deleted. Let's move it out of the picture. And now let's rearrange the picture. We have deleted the middle node and now we have pointer to the node on the left. And this node points to the node on the right. If P is none, P is not none. So we will not move into the body of the last if, and we will go to the last line which says return P. People might ask where R went. R fell out of scope when the function completed. So P is returned and the O notation is 1. Now we assume that the node pointed to by self is the first node of the DLL. Again we arrange PQR in the same way. P points to self.left, but self.left is none, so P is none. Q is self. R points to self.right. If P is not none, but P is none, so we don't go into the body of this if. If R is not none, this is true. R dot left is P. Make the left of R point where P points. But P is none. It does not point to anybody. So the left of R becomes none. Now look at what has happened. Look at the node which is pointed to by self. No node in the doubly linked list is pointing to this node. So this node has been deleted out of the doubly linked list. Let us remove this node. P is none. So we will move into the body of the last if, where we are being asked to return R, which we return. P perishes as it falls out of scope. The O notation is 1. Finally, we look at the situation where the node pointed to by self is the last node of the DLL. And we are supposed to delete it. Again, we arrange PQR. P is self.left. So it points to the node on the left of self. Q is self. R is self.right, but there is no node on the right of the node pointed to by self. So R is none. If P is not none, this is correct. This is true. P dot right should point where R is pointing. R is none. So P dot right will be none. If you look closely at the picture, you will realize that the node pointed to by self is not being pointed by any node of the doubly linked list. And it has been deleted. Remove it out of the picture. This is what you get. If P is none, this condition is false. So we will not move into the body of the last if. We are going to return P. When the function falls out of scope, R will perish. We return P. And the O notation is 1. Now we implement the len function for the doubly linked list. It takes pointer to any node in the list. So this is our list. Self points to the middle node. Place A where self is pointing. Take a variable I, initialize it to 0. Run a while loop as long as A is not none. So A is not none. What do? Increment I and advance A towards the right. A is not none. Increment I. Advance A towards the right. A is not none. Increment I. Advance A towards the right. Now when you do this, the node to which A points has right pointer equal to none. So A will become none. Now when you check the condition of the while, it is false. So you come out of the while. Then you set A to the left of self. Again you move into a while loop whose condition checks if A is not none. The condition is true. Increment I. Advance A towards the left. A is not none. Increment I. Advance A towards the left. Look at the node to which A is pointing. Its left pointer is none. So A will become none. When A becomes none, the while condition becomes false and we come out of the second while. Then we return I, which is the number of nodes. The O notation is obviously ON because we have visited n nodes. Now we take a look at the traverse function for this class. What we want to do is we want to print out the elements of the doubly linked list the way they are stored in the doubly linked list. For this reason, when we are given the self pointer, we move it all the way to the extreme left and then we start reading the nodes until we get to the extreme right. This is what happens in the code. A is set to self and then we move A towards the left until it reaches the extreme left node of the doubly linked list. Then we start printing the elements of the nodes until we get to the extreme right node in the doubly linked list. I want you to draw step-by-step pictures depicting how this function would execute. In the worst case, we will have to move 2n times. The worst case would be when self points to the extreme right node. Then we will move all the way from the extreme right to the extreme left. And then we get to the extreme left, then we start printing the values of the nodes. So this will be n movements from right to left and n movements from left to right. Twice of n, the O notation will be n. Now we look at the search function. We are given pointer to a node in the doubly linked list self and we are given a target value. We set B to self and while B is not none and B dot data is not equal to target, we advance it towards the right. We can come out of this while loop in one of two conditions. We can come out if B is none. This means there are no more nodes in the right direction. And we can come out of the while loop if the node we are standing on contains the target element. Now when we come out of the while loop, we first need to know why we came out of the while loop. So we check if B is not none. If B is not none, this means that we came out because the node we are standing on contains target. In that case, we return B. Otherwise, we know that there is no node that contains the target on the right side. So we take B back to not self but to the left of self. Then again we use a while loop which works as long as B is not none and B dot data is not equal to target. Again, we can come out of this while if there are no more elements or nodes on the left, or if the node we are standing on contains the target. Inside the body of this while, we advance B towards the left. When we come out of the while, we return B. Either B is none, which means that the search has been unsuccessful, or B points to the node containing the target, which means the search is successful. Draw step-by-step pictures depicting how this function would execute. And the O notation of this function is ON. In the worst case, you will have to look for the target in all nodes of the Doubly linked list. We have created a class for the Doubly linked list. Now we are going to use the class. So we import it in a new file. We are going to build a Doubly linked list towards the right. The function is called buildListWrite. It takes an argument val, which is a Python list containing the data we want to store in a doubly linked list. Val must have one or more elements. So we write assert len val is greater than 0. Otherwise, we tell the user that there are no elements to store. We create a node and put val 0 in it. A pointer A points to this node. The code is A equals DL node val 0. A for loop runs from 1 to n minus 1 for I in range 1, len val, 1. Inside the loop in iteration I, we insert a node containing val I to the right of A. We use the insert right function, a.insert right val I. Then we advance A to the right, A equals a.right. When all elements of val have been stored, we come out of the loop and return A, which now points to the extreme right node because it has been shifting. So we return A. This is the end of the code. Draw step-by-step pictures depicting how this function would execute. Even without the pictures, we can see that the function is ON because there is a for loop which is running from 1 to n minus 1. It runs n minus 1 times. The O notation is ON. We want to build a doubly linked list towards the left. The function is called buildListLeft. Well, write the body of this function. Return a pointer to the list. Analyze the function for time complexity. So what did we learn today? We were introduced to circular singly linked lists. We implemented functions for circular singly linked lists. We were introduced to doubly linked lists. We implemented a class to create and manage a doubly linked list. We saw pictorial depictions of code fragments. We learned how to build a DLL. And we found time complexities of all codes. So once again, read the book, note your questions and put them up in the relevant online session. Email your suggestions to me. Please do all the homeworks that I have assigned to you regarding linked structures, because if you do not practice, you will not be able to understand these concepts in a clear manner. Take care. Allah Hafiz.